Hey guys, we're going to talk about reaction mechanisms next, almost to the end of Unit 5. And we've touched on these through several different conversations as we've gone through Unit 5, and we've touched on them as we talked about catalysts and as we've talked about reaction coordinate diagrams. So we're going to go ahead and jump in and finish up our conversation about reaction mechanisms. And then we'll talk about catalysts. So switch here, can. Okay. All right, so reaction mechanisms. So what is a reaction mechanism? A reaction mechanism is a set of steps that try to explain how a reaction takes place. And really, honestly, this is just our best guess for how a reaction takes place. So we talk about chemists' intuition. Um, and they can be supported by experimental evidence. So, what is the mechanism? This is the set of bond making and bond breaking steps that lead from our reactants to our products. We tend to study rate in order to find information about these reaction mechanisms. So we have to experimentally validate these mechanisms. So we test by adding and removing components of the equation. We test by changing concentrations and seeing what happens to rates. So because a mechanism explains the steps that happen along the way, we have different types of steps of our mechanisms. So we have our fast steps, and our fast steps are those steps that are not rate determining. And then, of course, we have slow steps, and slow steps are our rate determining steps because the whole reaction can only go as fast as the slowest step. And then we also can have equilibrium steps within a mechanism, and our equilibrium steps can sometimes be rate determining. So our rate determining step is either going to be a slow step or occasionally an equilibrium step. And just a reminder that an equilibrium reaction is one where reactants form products and products form reactants at the same time. And once we reach equilibrium, that happens at the same rate. But we also remember, hopefully from honors chemistry, that if we remove one of these, if we remove some of our reactant, that the product will push forward and make more reactant. And so if we have an equilibrium step, it generally is going to go as fast as the step after it, because as we remove reactant, more reactant is produced. So how do we know if a mechanism is correct or not? We have two tests that we put to a mechanism to see if that chemist's intuition, if that best guess is correct. The first one is pretty self-explanatory. The sum of the steps has to produce the net equation. So whatever steps we think are occurring along the way, if those steps don't lead from reactant to product, that's not a good mechanism. And then our second step is that the rate laws of the rate determining steps get combined to produce that experimental rate law. So our experimental rate law is really our number one tool for determining whether or not a mechanism is valid. If the rate law matches up with what we think the mechanism is, then that's a pretty sound endorsement of that particular mechanism. They can also be confirmed by seeing if the presence or the absence of a species changes the rate of reaction. So, for example, in the decomposition of ozone, chlorine is a catalyst. Actually, monatomic chlorine is a catalyst. So our mechanism says that chlorine is needed in the slow step. So that tells us that if removing chlorine slows down the reaction, that's a way that we can confirm that mechanism. Okay, so just a reminder, rate laws do not use the reactant coefficients of the balanced net equation, but they do use the reactant coefficients of the balanced rate determining steps. And the rate equation for any individual step is defined by the stoichiometry of that step. And we talked about that when we talked about elementary reactions, that we were able to write a rate law for each step. We're just taking this one step farther. So before we jump into writing rate laws and validating mechanisms, let's talk about intermediates and catalysts. So an intermediate is something that is formed in the process of a reaction and then consumed in a subsequent step. So intermediates only occur in multi-step reactions. You should be able to identify the intermediate if you're given the steps. So for this reaction, we have hydrogen reacting with nitrogen monoxide to give us nitrogen gas and water. So we're given this mechanism and we're asked to find which species are the intermediates. So the intermediates are going to be the species that show up as a product in an early reaction, but then are consumed in a later reaction. And so we can see this dinitrogen monoxide shows up as a product of step 1, but then it's consumed in step 2. And so we would say that the dinitrogen monoxide is an intermediate. So intermediates show up as a product, get consumed as a reactant in a later step. That's an intermediate. Let's talk about a catalyst. So a catalyst, on the other hand, tends to be used in an early step, then it gets produced in a later step. So a catalyst very often does react with our reactants, but it's regenerated. So catalysts aren't consumed overall in the reaction, but they're consumed early and regenerated later. So again, we're given a mechanism. We have chlorine reacting with ozone to give us oxygen and chlorine monoxide, and we have chlorine monoxide reacting with oxygen to give us chlorine and oxygen, monatomic chlorine and oxygen. So we can see that chlorine here is a catalyst. It is consumed in the first reaction. It's regenerated in the final reaction. We can also see that this reaction produces an intermediate. We have this chlorine monoxide that is produced in an early reaction and then consumed in a later reaction. So this reaction actually has both catalysts and intermediates. And most reactions that have catalysts do have intermediates, and those intermediates generally do involve that catalyst. Okay, so now let's talk about these multi-step mechanisms. Just a reminder, any multi-step process, one of the steps is going to be slower than the others. So just like driving into Norfolk, we all get slowed down by the tunnel. Our reaction is going to get slowed down by that rate determining step. If we are given the information about the rate determining step, so we're given this reaction, we're told that step 1, the nitrogen dioxide reacting with the fluorine to form nitrogen dioxide monofluoride and monatomic fluorine is the slow step. From that, we can write a rate law for this mechanism, and our rate law would be the rate with the coefficients from the slow step. So our rate here would be rate equals K times the concentration of NO2 times the concentration of fluorine, both of them raised to the first power. So this would be first order with respect to nitrogen monoxide and fluorine, and it would be second order overall. Okay, so our rate laws are always going to reflect the chemistry of the slowest step in a multi-step reaction. They may also reflect the equilibrium chemistry that occurs prior to the slow step. So what do we do? How do we write a rate law if all the steps are the same speed or if the slow step contains an intermediate? Because for College Board's purposes, we don't want to have intermediates in our rate laws. So we're going to use what College Board calls the steady state assumption. This is actually a major oversimplification of the true steady state assumption, but we're going to work with it. So as an example, we have this reaction where hydrogen iodide reacts with chlorine to give us hydrogen chloride and iodine. Missing a 2 there, sorry. So this occurs by this mechanism where chlorine reacts with hydrogen iodide to give us hydrogen chloride and iodine monochloride, and that step is fast. And then our second step is our slow step. And our second step is iodine monochloride, that intermediate, reacting with hydrogen iodide to give us iodine and hydrogen chloride. So I would write the rate as rate equals K times iodine monochloride concentration times hydrogen iodide concentration. But we can't have an intermediate in a rate law. So what do we do? How do we get rid of that intermediate in the rate law? We're going to treat the first step as if it's an equilibrium reaction. So we're going to just rewrite it with that double-headed arrow. And we're going to treat the second step as the slow reaction. So that still looks exactly the same. Now, in an equilibrium reaction, the rate of appearance equals the rate of disappearance. And so we can write that the rate of appearance equals the rate of disappearance. And so we're writing the rate of the forward reaction, and then we're also writing the rate of the reverse reaction, and we're setting them equal to each other. And we're going to rearrange that to solve for that intermediate. So now we know that the concentration of iodine monochloride is equal to some K times the concentration of chlorine times the concentration of hydrogen iodide divided by another K times the concentration of hydrogen chloride. So now we have something that we can substitute back into the rate law that we had written. Rate law equals K times this intermediate times the concentration of hydrogen iodide. And we're going to sub that in. Here's our substitution for our iodine monochloride concentration. And that's what we figured out on the previous slide. This comes from the idea that the forward reaction and the reverse reaction are the same speed. Now, this is a constant, this K sub -1. This K1 is also a constant, and this K is yet another constant. So we're just going to combine all of those into this K prime, which we'll wind up just writing as a K. Sorry, I seem to have lost a bracket. So we'll have the concentration of chlorine times the concentration of hydrogen iodide times the concentration of hydrogen iodide divided by the concentration of hydrogen chloride. So we would eventually write this as K times chlorine concentration times hydrogen iodide concentration squared divided by hydrogen chloride concentration. So it's a very messy rate law, but it is a rate law. And this is how we can occasionally wind up with rate laws that are fractional, that have both numerators and denominators. Okay, so the rate of our reaction is always going to be limited by the slow step in the mechanism. And our experimental rate law, that thing that we determine from experimentation, shows those species upon which the reaction rate depends. If the species in the rate law are the reactants with the appropriate coefficients in the slow step in a proposed mechanism, it's evidence that that proposed mechanism could be right. So that's what we're going to use to determine if a possible mechanism is correct. So if we're looking at this reaction, carbon monoxide, nitrogen dioxide, carbon dioxide, and nitrogen monoxide, we experimentally determine that the rate law is R equals K times nitrogen dioxide squared. Okay, so that tells us that the slow step must have 2 nitrogen dioxide molecules and nothing else, because there's nothing else in this rate law. So we're going to look at possible mechanisms. So the first possible mechanism is that it's a single step. Nitrogen dioxide plus carbon monoxide makes nitrogen monoxide and carbon dioxide. And the rate law for that would be K times the nitrogen dioxide concentration times the carbon monoxide concentration. because that does not match that experimentally determined rate law, this isn't right. That mechanism is not correct. Okay, we have another possible mechanism. We have the idea that nitrogen dioxide could dimerize to give us dinitrogen tetroxide. That could then react with carbon monoxide to give us carbon dioxide and nitrogen monoxide. And we would be producing this intermediate of the dinitrogen tetroxide. So what would the rate law for this look like? Well, now we've got an intermediate, so we're going to have to do a little bit of extra work here. So we're first going to write that slow step rate, and that's K times the concentration of dinitrogen tetroxide times carbon monoxide squared. And we then use our steady state assumption to find that the rate here would be the rate of nitrogen dioxide squared times carbon monoxide squared. And that doesn't work because that doesn't match up with our rate equals K NO2 squared. So that mechanism is out. Let's try one more mechanism. This mechanism says that two nitrogen dioxide molecules combine to form a nitrogen trioxide and a nitrogen monoxide, and that is a slow step. And then we have the nitrogen trioxide, that intermediate, reacting with carbon monoxide to give us nitrogen dioxide and CO2 as a fast step. So slow step, we would use that to write our rate law, and we would then write rate equals K times NO2 raised to its coefficient, which is 2. That matches up with our experimentally determined rate law, and so we would choose this as our valid mechanism. As always, if you have any questions, let me know.